Now we've covered the basics of plotting and we've written our skeletal code for ODR, we're now ready to apply this to some data that we have here, and we'll attempt to fit a linear line to it here. So first of all, we'll start off by commenting this out because we're not quite ready to use the fitting yet. We're just going to generate a plot first and then we'll apply the fit to it. So as before, we can proceed with code that we used in the very first video, although I'm going to use another argument here called fig size, which just changes the size of the plot. You can play around with that. If you want a bigger or smaller plot, then that'll come in handy. As always, we'll have a nice high DPI. So we'll begin by plotting a scatter. So we've got our X data, we've got our Y data. Let's choose a marker as X. Let's choose small line width. And let's choose our label as observed data. Okay. Now we can plot our error bars. So again, we've got X data, we've got Y data. Our X errors are called X underscore error up here, similar with the Y error. Let's choose the line style to be none. Okay, let's just zoom out a bit. Okay, here we are. So we've got our error bars plotted. Let's set a title quickly. Okay, and let's set our legend. Because remember, we've got some labels that we've defined here. So we need to remember to place our ax.legend. Remember to place it at the bottom, because if you place it above, say, this line of code, then that label won't be included. So if you want all of them included, make sure to place ax.legend above all of the plots and error bars and whatever you're going to use labels for. So we've got ax.legend, lockers upper left, and then let's make it slightly smaller. Okay, and then as always, we'll end it with ot.show. Okay, so let's see if we get a decent plot. Here we are. Okay, so this clearly looks like a linear relationship here. Now we're ready to proceed with ODR. Okay, so let's continue. We'll uncomment this. So we've got model is model fit. That's the right name. We've got the correct definition of our model because it's a linear line. So we've got an intercept and a gradient, and it's going to take in our X data. So we're writing the Y data as a function of X as beta 0 plus beta 1 times X. ODI is going to solve the parameters for us. It will return the best fit parameters with some errors. So let's check it line by line. That's correct. Data equals real data. We've got X, we've got Y. We've defined our X errors and our Y errors up here. So that's all good to go. So ODI equals ODR. We've got data, model. Now we need to define our guesses. So if we just extrapolate here, we could say the intercept is probably around 1, around there, halfway between 2 and 0. So let's say guess 1 is 1 because that correlates to this here, which is our intercept. And then guess 2, what would that be? Well, let's just take a guess. Be around 2, I reckon. So remember, you can always change these. You just need a rough guess to begin. So ODR fit type, let's leave that as 0. Okay, so we're all ready to go. So if we just click run. Right, here we are. It's a bit small. I will zoom in. Okay, so this here is our beta array, which contains our best fit parameters. So the first one is our vertical intercept, and the second is the slope, or the gradient. And then under here, the beta STD error is the corresponding 1 sigma standard deviations, or the errors in the determined parameters. And right here it says reasons for halting, sums of squares convergence. So that means it's obtained the best fit. If you have any other reason, that might not mean that it's determined the best fit. But sums of squares convergence means that you've determined the best fit possible. So now that we actually have our best fit parameters, let's plot it and see if it actually looks reasonable. So what we'll do here is I will just move the ODR code above, and then this will allow us to plot it using the determined parameters. Because once this block of code is ran, we will then have determined the beta matrix containing our best fit parameters, and then we can use that down here to plot it. Because of course, if we tried to plot it first, we wouldn't be able to, because we wouldn't have determined the parameters, so it would have to be under it. So as before, we'll do x.plot, so out of x, and then we'll call model fit, and we'll give it beta and x. So this is just saying, let's plot x, and then let's plot the best intercept plus the best slope multiplied by x. So remember, that's not quite the same as y, because y is the data here, but model fit beta x is the y predicted by the model that we're trying to fit to the data. And then let's say color is red. Now let's label this something like best fit. Okay, and remember what I said before, the legend has to be under all things with labels. So if we put the legend here, and then we run this code, okay, that looks like a reasonable fit. What we could also do is plot the best fit line plus the 1 sigma uncertainty and minus the 1 sigma uncertainty, which gives you a 1 sigma confidence interval. So we might have a slightly steeper line, and then a slightly shallower line, and then in between those two is the 1 sigma confidence interval, which you can highlight and shade in. So we can start off by defining something like yFit add error. So this will be the same model here, but we will add beta error 1. So this is going to be the same line plus the error. Remember, we've defined beta error here as output.sd_beta, so that has been assigned to these numbers here, the corresponding 1 sigma standard deviations, and then we can similarly define another line like yFit subtract error. This will be the same, except it will be beta 1 minus beta error times x. And then again, we can just plot those two lines onto the same. So instead of model fit beta x, we will have yFit add error. So, oh, not that one, let's do that one. I don't know, let's set that as green. Let's call this best fit plus 1 sigma. And then we can go ahead and do the same line as before. yFit subtract error. What color do we want this to be? Orange. This will be best fit minus sigma. Okay, let's see what that does for us. Okay, as you can see, there's quite a small uncertainty, but you'd expect that. But you can still see here. So here we've plotted the best fit line plus the uncertainty and the best fit line minus the uncertainty. And the line of code we use to shade in between two lines is right here. So it's called fill between. So the first argument is our x data, and then the next two arguments are the two lines that you wish to shade between. So here we've got y-fit add error and y-fit subtract error, which we've defined up here to be plus the uncertainty and minus the uncertainty, respectively. So that will shade in between the steeper line and the shallower line. And then alpha is a parameter between 0 and 1, which determines the transparency of the shade. So I usually go quite low, say 0.3. Cyan is quite a nice color for this, and we can label this the 1 sigma confidence interval. And once upon adding this line of code, your plot will then have a shaded confidence interval like this. Of course, you can use this for any arbitrary function. So let's say if you had a quadratic, you can just trivially extend this to plus beta 2 multiplied by x squared. If you had a trig function in there, maybe a sinusoid, you could have plus beta 3 times np.cosine x, and as you can see, you can just keep adding functions as you need them, and wherever you have a parameter, you can just add beta and then square brackets, whichever number, because you have to increase them in order. So if you start at 0, then 1, 2, 3, and so on and so forth. So you can do this for, like I said, many functions. I've done this in my lab modules for not only linear fits, I've done quadratics, I've done exponentials, sinusoids, all sorts. So I hope this little series has been helpful. I hope it's given you a basic understanding of how to use Matplotlib to make some plots and to visualize data, and how to use ODR to conduct some model fitting. I've only scratched the surface here. There are many other arguments in all of these lines here to customize your plots. You can add grids, change the size and the colors. You can even add LaTeX output to typeset equations in your captions and labels. I myself have done that for labs. I can show you how to do that if you'd be interested. I'll show some of my LaTeX plots on the screen now. So if you'd like to know how to make figures like that, then do let me know and I will get on to making a video on that. So I hope this series has been helpful, and I'll see you in another video.